And I'm recording. Why don't I share? And we'll be on my pseudo whiteboard here in a second. So make sure you have some paper to record notes, because we're going to be doing kind of like reactions and mechanisms here in a couple of minutes. All right. All right. So we're on the kind of the end of the chapter 13 PowerPoint. We already did this stuff on the acidity of alkynes. Chapter 13, of course, is the alkyne chapter. Chapter 12 was the alkene chapter. But we went back to the chapter 10, which is the NMR chapter. So chapter 12 was an organic 1 chapter, obviously. So the exam is technically it would be next Thursday, but because of the transition back to face, I'm moving it to the following Thursday. But as of this weekend, I'm going to have up the exam 1 materials. I hope. I think I should be able to have the exam 1 materials up on the website by this Friday afternoon, and so you can kind of get ready for exam 1. If you can get really good at exam 1, and then the real exam 1 will come around, that'll be a good precedent for the rest of the course. All right. Okay. So yeah. Basic gist of this is that the terminal proton of an alkyne is really acidic. 25 is, do I share past exams? So I give you a good representative exam. Some of it may be a previous exam. So I give you one good exam, yes, and it'll be a pretty representative thing of what you're going to see on the real exam. Knowing the broad materials, and I give you a study guide and everything like that, that'll help too. Should be adequate, and also asking questions in office hours. Make sure that everything on the practice exam is like solid, and if you come to office hours, I can kind of figure out what you know and what you don't know, and what you don't know I'll help you with. We'll have real office hours by next week when everything's face to face. Super useful, because we often do it in big groups, and you can meet people and study partners and stuff. So it's really cool. All right, so yeah, terminal proton of a alkyne is super acidic, 25, and it was something about the sp hybridization of the carbon, and lots of s character. S character corresponds to electrons that are kind of on that carbon, right? They're close to the carbon, and it stabilizes a negative charge. So when you pull off that proton and you get a conjugate base, the conjugate base is sort of stabilized. And that's why the pKa is kind of low. So terminal alkynes, you can rip off the proton with a good base. A couple of the bases are like lithium, butyllithium. Butyllithium is a really good base, and that will take off the proton. How would I draw the mechanism? I usually would circle the line to the lithium, and then go grab the proton, break the bond onto the alkyne, and then you get essentially an alkyl lithium. It's kind of like organic 1 times, right? Like a Grignard or organolithium. And of course, that thing is a nucleophile, so you go attack stuff. So that'll be part of the whiteboard presentation in a second. Okay, NMR. This is fun. Hopefully you're all experts in NMR now. Let's talk about, well, we know alkenes a little bit. We talked about alkenes, and then we'll generalize that to alkynes. All right. So what's the chemical shift next to an alkene? Anybody know? If you have your chart semi, tattooed on your hand or ingrained into your brain from the syllabus, next to a pi bond was what? It was between what ppm range, roughly? Next to a pi bond, right? Not 7, but somebody said 2 to 3. Yeah, 7 is aromatic, and you might be thinking about these aromatic CHs. Yeah, those are 7-ish, but next to a pi bond is the 2 to 3 range, right? And that's totally 2 to 3 here, next to a pi bond. But what about the alkene? There's like 3 CHs, right? 1, 2, there's 3 of them. Those ones are not in the aromatic region either, but they're maybe at a little under 7, like kind of 5-6 or so. 5-6. They already shielded by the alkene, all right? Okay, so this one, what do you think? It's next to a pi bond. It's alkyne's a pi bond, right? 2 pi bonds. So any guesses? 2 to 3. 2 to 3, absolutely. 2 to 3 is next to a pi bond, right? So, and then you might think, oh, alkyne, alkene, same thing, kind of, right? You might think that, but it's not. The alkyne is weird, and it actually is kind of extensively shielded, and so it's actually around 2. It's weird, and there's something about the flow of the electrons around the alkyne. There's little figures that explain this, but we don't really get into that. But a alkyne CH is 2, whereas an alkene, all the alkene CHs are actually kind of de-shielded. That's weird. For now, I would just take my word for that. And in the chapter 13, there's a couple homework problems where you solve NMRs of alkynes. And you'll see that. You'll see a weird proton at 2, and you're like, and you kind of, you figure out, oh, it's a terminal proton and an alkyne, okay? Why is it shielded? I think there's a figure on that. You can go look. I'm not going to really address the reasoning for it, but you have to agree it's a little weird, right? Alkynes at 2, alkenes at 5 or 6, you know? Okay, here's a question for you. Without NMR, how do you know you have an alkyne in your molecule? So if I give you an NMR spectrum, without even really thinking about the NMR, what would be a requirement if it is an alkyne? Any guesses? Like this molecule here, just pretend it's this molecule. Any information that's not in the NMR, maybe molecular formula, that would be a good hint that you have an alkyne. Let's just think about this alkene real quick. But let's go back to the alkene. What's the degrees of unsaturation? Just looking at the molecule. How many degrees of unsaturation are in the benzene? There's a ring and 3 double bonds. So thus, the benzene has 1 plus 3 equals 4, right? A benzene has 4. And the alkene would be 5, right? Because that's a double bond. So 4 plus 1 is 5 UN, right? Degrees of unsaturation. But in alkyne, how many double bonds are there? You have a single bond and 2 double bonds. Thus, UN of this molecule is? So now how many double bonds are there? There's a single bond and 2 double bonds, thus 2. And so how do you, so back to the question, how do you know you have an alkyne in your molecule? Without even looking at the NMR. Before you even do the NMR, you look at the molecular formula. With the molecular formula, you figure out the UN. And if you see a UN equals 2, you probably immediately say, must be an alkyne, right? That would probably be the assumption. Now, what if it's UN equals 6? Maybe you have a benzene and a alkyne, right? 4 for the benzene, 2 for the alkyne. Like if this was an alkyne over here, instead of an alkene, UN would be 6. 4 plus 2, right? Okay, so can I explain one more time? Yeah. Okay, so of course, this molecule on the left is easy, right? UN, again, UN is rings and double bonds, right? So the benzene is 4. You got a ring and 3 double bonds, right? A ring and 3 double bonds, that's 4. The alkene would be a 5th one. 4 plus 1 is 5, right? And over this molecule over here, this simple alkyne, the triple bond acts like a single bond and 2 double bonds, right? A single bond, like the middle one, I guess you say, and then the 2 double bonds. So that's a total of 2 double bonds. And each double bond is a UN. So UN of this molecule is 2, okay? So a random alkene will have UN equals 1. Random alkyne will have a UN equals 2. And so when you see UN equals 2, you immediately start thinking alkyne, 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 right? That would be a good indicator that you're going to have an alkyne in your molecule. Okay, good. Okay, so then this is the other kind of crazy thing about alkynes. Um, Remember complex splitting? Hopefully we talked about it a little bit, doublets of triplets and doublets of doublets and stuff. The main reason we had complex splitting, you may have to review that lecture in the NMR stuff, was because you had two different J values. Like I have a CH and it's like talking to a neighbor at J equals 7 and another neighbor J equals 2 or something like that. That would be complex splitting, like, right? Do you remember what the default J is? The default J, like random, a J in a molecule, is not 2.5. It's, anybody remember? The default J is always 7, 7-ish, 7.5. Yeah. So when you see this 2.5 here, that's weird, right? Okay, so, and also check it out. It's a triplet. Why is it a triplet? Because how many neighboring, the rule is neighboring CHs. How many neighbors are there here on the neighboring carbon? Well, technically there's 0 neighbors. The neighboring carbon has 0 H's, right? So why is it a triplet? And why, it actually sees through the alkyne to the other side. The CH sees through the alkyne to the other side and sees 2 neighbors on the other side of the alkyne. 2 plus 1 is a triplet, okay? That's weird because it kind of violates our understanding of the n+1 rule because we always said neighbor, and the neighbor is this. Then carbon has nothing on it, so it's weird that it's triplet. Okay, what about this guy? What about this CH2 right over here? Any ideas what kind of splitting it's going to have? What kind of splitting? Is it a doublet or triplet, a quartet? Anybody know? I mean, how many neighbors are there? Yeah, it's a triplet. Yeah, it's a triplet. And what's the J value going to be? Default J, 7-ish, right? Triplet 7. Okay, now something weird's going to happen because this guy sees a CH2 in one direction, which could make it a triplet, but it would see a CH on the other side, which would make it a what? What if it sees a CH, one thing on the other side? It's going to be a triplet because of this side and a doublet because of this side. But since they have different J values, it's that funny thing called complex splitting. And this is the doublet of triplets, okay? Why is it a doublet? Because it sees a CH. Why is it a triplet? Because it sees a CH2 next door. That's the general phenomenon of complex splitting, okay? This is what the NMR actually looks like, for the whole molecule. What are these different things? Well, we have something of 9. What's 9? That's easy, right? That's the 3 methyl groups, right? Singlet. Why is it a singlet? Because there's no neighbors, right? Then you got this triplet of 2H, with a big J value. Triplet is a triplet, right? 2H because there's 2 protons. And it's a big J value because you can see the large distance between the legs of the triplet. Which one is it? Which box? Left, middle, or right box? It's a triplet. It's 2H for 2 hydrogens, right? I see middle, left, and right. Well, okay, so it's a triplet. So it has to be either the left one or the right one, right? And if you look at the distance of the legs, it's actually kind of a big difference. Whereas like this triplet's a really small distance, right? That's going to be the small J, this is going to be the big J. So this one is actually the triplet on the left. And that's because, I mean, it's a CH2. There's also, the chemical shift. 1.4 is kind of the boring, nothing nearby range. So it's in the 1 to 2 range. And that makes sense because it's not next to the alkyne. It's kind of far away from it, right? And then this, now we have the small triplet of 1 proton. Oh, so it has to be 1 proton. So is that the left box, middle box, or right box? Single proton. Single proton. What would correspond to a single proton? A CH2, a CH2, or a CH? Single proton. Small J value, like in that 2.5 range. That's totally the right box. This is the terminal proton on the alkyne, right? The terminal proton on the alkyne has a small J value, which is weird because it's communicating over a long distance to the CH2. And then what's this weird thing is doublet of triplets. It looks like a triplet where every leg is a doublet. Is that the left, the middle, or the right? And of course, that's the middle. Okay. And somebody said definitely left, and that's not left. The doublet of triplets obviously is right here, and it's the green box, doublet of triplets, DT, and that is the one. Okay, you're scaring me. Somebody's joking around here. Yeah, definitely it's the middle one. Okay, so there's a couple takeaway messages that might be useful, maybe good notes. Especially as you struggle with your first alkyne NMR problem, you very likely will have an alkyne NMR problem on the exam. So getting some of these rules down now on your notes would be useful. One rule is first rule, UN has to be 2, right? UN of this molecule is 2. That's a good rule. Second rule, when you do have a terminal alkyne, yeah, like this terminal alkyne, which of the signals is going to have a small J value in terms of the molecule? The molecule, when you have the molecule, you have a small doublet or triplet or something with a small J value, that's going to be the terminal alkyne. So small J value, small, like 2.5 hertz. And I'd always tell you 2.5 hertz or 3 hertz or something. That is the one that's the terminal alkyne. And which is going to be the signal? If I just look at these signals, the one that's next door to the alkyne, but it's not on the alkyne, is the complex multiplet, which is like a doublet of triplets or something, right? A doublet of triplets would always be the signal that's next door to the alkyne that's not on the alkyne. It's like that CH2 is different than like this CH, okay? Those little tricks will get you through the hardest possible problem. And you'll have practice on the sample exam. So if you struggle, keep those tricks in mind, right? Okay, good. So that should be enough for this. Couple random alkynes in drugs and stuff. Norethynadril is a steroid molecule. It has an alkyne in it with an alcohol. This was the part of the first oral contraceptive, and a lot of the steroids. Okay, so somebody said, can you explain again why the H in the right does long distance coupling? Let's go back. Why the H in the right does long distance coupling? This one, you mean the alkyne CH? I think that's what you're asking, is why does this alkyne CH have long distance coupling? Well, the answer is alkynes are weird. It's just a kind of a weird alkyne thing. Alkenes don't do this. It's something about the angles and coupling, doublets and triplets. There's definitely a geometric effect. There are molecules where it'll be long distance, like 5 atoms away. So this is not even that crazy. I could give you examples of like super, super, super long coupling. But for now, we'll say, truthfully, the only example of long distance coupling is alkynes. Because our other complex multiplets was not long distance. It was just an aldehyde. Aldehyde next door did this also. But this is a kind of a long distance effect. I don't know, just somehow the angle of it just feels the effect of that CH2. Yeah. So weird. Okay. Okay, so yeah, steroids are often involved in contraception medicines, and this alkyne, I think, I don't know, I don't know the exact reason it's there, but it kind of mimics the effect of like some of the female reproductive hormones, and And this is a non-natural steroid derivative that was used as a contraceptive. And then here's an HIV reverse transcriptase inhibitor. One of the cool ways that, maybe one of the earlier ways that we treat HIV by inhibiting a protein called reverse transcriptase. There's a whole cool story about how that works. Am I done with this? Oh, more. Haha. This crazy molecule, calicheamycin. It's a enedione. Why do you think we call it an enedione? Well, because it has an alkene and two alkynes. These are weird antibiotics. It's a whole class of natural molecules with a very crazy structure. It's like just other stuff. A methyl with 3 sulfurs. You know what a disulfide is? Any guess what this is called? It's called a trisulfide. There's very rare cases of trisulfides, especially in naturally occurring molecules. Also, a random iodine in a molecule. You know, most natural molecules don't have iodines in them. This, I think, is like sponge derived, like from a, you know, in the ocean. But the enedione, this is kind of why it's an antibiotic and how it kills bacteria. It does something kind of cool. It gets activated maybe inside the cell, but the 2 alkynes cyclize to form a benzene diradical, an aromatic diradical. And of course, these radicals are super, super unhappy and unstable. And they just start ripping on the atoms, ripping off hydrogen atoms and things from inside the cell. And this is basically how it acts as an antibiotic, basically from this crazy destruction of the internal structure of the cell. So yeah, the Bergman cyclization is a kind of a weird reaction that occurs on enediones, like this enedione antibiotic. Okay, cool. Are we done with this chapter? Now, not the chapter, but now we're ready for the whiteboard attempt. All right, here we are. We're getting into the reactions of alkynes now. It's a little blurry, but I'll kind of draw big to make it all work out. So 1 through 3 of this chapter 13, that was all the PowerPoint, right? So we're on to number 4 now. And I always try to do this sort of structured delivery of lectures. So each of the parts will be a kind of like a heading. So we're on to the first thing, of course, you should ask yourself is how do we make alkynes, right? Preparation of alkynes. How do we prepare alkynes? Most of the chapters in this course will be like, how do you make something? And then what can you do with it? So one of the ways is the double elimination method. Double elimination of 1,2-dihalides. Dihalides. Of course, a 1,2-dihalide would be a carbon with like 2 bromines or something like that, right? So the basic idea of this, we'll just demonstrate. So if I have like an alkene and I want to convert it to an alkyne, it seems kind of weird. How do we convert an alkene to an alkyne? Well, what we can do is essentially first brominate it, Br2. Brominate the alkene. That's actually chapter 12 stuff, organic 1. And then we're going to treat this with a base, NaNH2. Okay, so what does this all do? And here's the product. Anybody remember, you have to remember some of your organic 1 knowledge. What did Br2 do to an alkene? It converted it basically to a dibromide, Br2, right? That makes sense. You're going to make a Br and a Br. And what is the mechanism of that? So the mechanism, I'm going to try to do it in blue. I usually try to do my mechanisms in different colors, but the webcam, it may not come out totally clear. Okay, so when the mechanism for Br2 reacting with an alkene is actually first you form this funny three-member ring thing. I don't even remember that from your organic one. Anybody remember what it's called? It has a weird name. It looks like a epoxide almost, right? It kind of looks like an epoxide, but it's not an epoxide. It's got a bromine. It's a something IUM. Something IUM. Br, bromine, blah, 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 IUM. Bromonium, somebody said, and that's correct. Bromonium. So you make a bromonium, and then of course what we're doing is we're just making the Br thing. So now Br minus, you got lots of Br minus. This thing acts like an epoxide. This thing kind of acts like an epoxide. Acts like epoxide. And if you remember epoxides, they like to be attacked by stuff. Br minus, what's it going to do? Attack the bromonium. Circle lone pair on bromine, attack. Open it up. Now you got your dibromide. Okay? Okay, cool. Everybody cool so far? This is essentially organic one. And now the base comes in. Na plus NH2 minus. Na plus NH2 minus, which of course is the same as Na NH2, right? This is just a strong base. Na plus NH2 minus with these two lone pairs on there. Okay, so this is also organic one stuff. Essentially, we're going to take off this proton right there, and that's going to eliminate off the neighboring Br. Let's draw the H somewhere else. Let's put it over here. Okay, so we have an H. Okay. This is like chapter 7, I think. Chapter 7 of the book. Chapter 7, you might remember that if we have a base and a proton and a neighboring leaving group, circle the lone pair, attack the proton, makes a double bond, kicks off the Br. What does that make? It makes a alkene, right? That makes an alkene. So now we got a alkene. I kind of flipped over the molecule a bit. Essentially, right, we made a double bond, and the leaving group's gone, right? We still have the other Br. I flipped it over. How do we do it next? Na plus NH2 ... minus. Sorry, again, a little blurry, and I apologize for that. Na plus NH2. It's the same thing as what we have here, right? Okay, so it's a base. What are we going to do to go from this guy to the alkyne? Na2, sorry, NH2. Na plus, NH2 minus. We do the same exact thing. Same exact thing we just did, right? So circle the lone pair on the nitrogen. Okay, and yeah, yes, I can post the notes. Sure, yeah, I can post the notes later. Yeah, it might be tomorrow. And remember, we only have 1 week of this, so. And also, all of this is in the last year on the last year YouTube. So in very high resolution, much better than this. Okay. So yeah, this takes the proton, makes the triple bond, and kicks this off. Okay, so let's review the whole thing again. We made the bromonium, and then the Br minus attacked and opened up to make the dibromide. 1, 2, dibromide. And then we use the base to take off the proton, kick off the leaving group, and make a double bond. And then we did the same exact thing again. Grab the proton, kick in, kick off the bromine. All right. Okay, so yeah, I'll post the like as a PDF file or something these notes. Okay, and I'll try to draw bigger for the remaining lecture stuff too. This is a little small. Anybody remember from chapter 7 the name of the reaction? When you use a base to take off a proton, make a double bond, and kick off leaving group. It's 2 letters, a letter and a number. I heard proton shift. That's wrong. It's a letter and a number, not SN2, because that's a nucleophile attack. It's E2. This is the E2 reaction from organic 1. Okay, E2 reaction. All right, good. Somebody said E2. Good. Okay, so let's see another example. Okay, so we're still on number 4. So what this is cool, what's cool about this is it's now a nice method to basically go from an alkene to an alkyne, right? Like if I want to take this benzene with 2 alkenes, and I want to convert it to a benzene with 2 alkynes, what would be the reagents to do this? Well, you just learned them, right? First step is a blah, 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 and the second step is a blah, 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 right? First step, turn it into dibromide, right? Second step, use the base, the strong base, and then it does the double elimination. Double elimination, because we eliminate twice. So what's the first step? Something 2. Br2. And the second step, Na something something, Na something something. It was the base, Na NH2. Okay, good. I'm not going to do the full mechanism, but maybe we can just draw the dibromide. It's actually going to be a tetrabromide. 2 bromines on the left, 2 bromines on the right. That's a good start, but it's going to essentially be Br here, Br there, Br here, Br there. That's kind of like the result of step 1 here. Okay, cool. And like I recommend in organic 2 and also organic 1, as you learn these reactions, I kind of like, this is your first reaction from organic 2. I kind of like the idea of index cards where you might draw like the reaction, or maybe even the previous page, like the previous page, like this might be the front of an index card, and on the back of the index card you can have the detailed mechanism, and then you have something to study for the exams, because you're going to be tested on these mechanisms, right? And you'll see what the sample exam is going to look like here by the weekend. Anyway, I strongly recommend the index card method. Okay. Cool. All right. Number 5. That was 4, the double elimination method. So now we're on to another preparation of alkynes. Preparation of alkynes from alkynyl anions. Remember that concept from the PowerPoint? The idea that you can rip off the proton from an alkyne and make it into a negative charge, right? And of course, this is a great way to make alkynes also. This is a super cool reaction. This is a very unique reaction of alkynes because alkenes do not do this. Okay, so recall, so I'll try to avoid the blurriness. I'll try to draw kind of big. Alkynes can be deprotonated. Deprotonated. What does deprotonated mean? Deprotonated means take off the proton, right? You can basically, no pun intended, you can basically use a base to pull off the terminal proton of an alkyne. So let's draw a molecule and show that. This is something I want a real big nitpick of, and I just want to get it out of the way. Are there any bad ways to draw this molecule? Yeah, because I know some of you probably drew it the bad way. And you know what's the geometry of like this carbon to the hydrogen? Is it angled or is it linear? It's linear, right? This is a linear functional group. So what's the bad way to draw this? The bad way would be like that. Don't do this. You will absolutely get points taken off of your exams. If I ever see these, it makes me cringe. This is an alkyne is a linear functional group. That means that from here, from this carbon to where the hydrogen is 180 degrees, right? This is a linear arrangement. It's not angled like the way an alkene is. Alkenes do this, alkynes don't, right? So don't do this, all right? So don't do that. I promise you that a bunch of people will still do it. So get out of that habit now. If you are doing that, get out of the habit now. It'll help you. Okay, so anybody remember how I take off that proton? I just use a strong base. I can use NaNH2. NaNH2. We also can use butyl lithium. That's the one I showed in the PowerPoint. Both of these are nice bases that can take off that proton. What's the pKa of it? I think it was something like, I can't remember, 20-ish or so. 20-ish. pKa of 20. That's fairly acidic for a CH. Most CHs are like 50 or 60, right? So anyway, I'm going to draw a mechanism, draw my lone pairs. There's 2 lone pairs. And how do I do this reaction? The base takes the proton off. Maybe I circle the lone pair. I love circling lone pairs. And it just takes off the proton, right? 2 arrows. Base takes proton, bond breaks, push electrons onto the terminal carbon of the alkyne. And what do we get now? You got the alkyne, but now the proton's gone. And the way I like to draw this is now you have a dot dot negative. Dot dot negative. And what's the counter ion? For every negative, there's a positive. So if this is negative, then what is the positive thing? In this case, with sodium NH2 minus, maybe the positive thing should be sodium, right? So it's Na plus. So it's carbon dot dot minus, Na plus, carbon dot dot minus, right? Okay, so this topic is preparation of alkynes from alkynyl anions. This is the alkynyl anion. Alkynyl anion. And this thing is super reactive, and it's a nucleophile. Nuke. So one of the things I can do with, organic 1, what are the cool things you can do to nucleophiles? Well, you can attack alkyl halides, thing with the leaving group. So like, for example, I can attack bromopropane, Br, right? carbon dot dot minus Na plus. That's a spectator. And the carbon, this thing can be attacked by an SN2 reaction. So how do I do that attack? Negative attack. So this carbon is delta positive. This is delta negative, delta positive, right? Delta negative, delta positive. So what I do with my second color is circle the lone pair and go attack this carbon and kicks off the BR. Carbon attacks carbon. And now this thing will contain those 3 extra carbons. Okay. Notice how I drew this. I'm preserving the linearity. So this carbon to that carbon is 180 degrees. Okay, good. So that was that. Trying to avoid this mistake, the bent alkyne mistake. Okay. All right, so that was cool. This is one way we can build alkynes. What's the mechanism when a nucleophilic atom attacks a electrophilic atom and kicks off a leaving group? Not E2, but something 2. Organic 1. A nucleophile attacks carbon, kicks off a leaving group. Something 2. It's SN2. That's right, SN2. This is chapter 6 stuff. Okay, one big rule about this. The alkyl halide, RX is the bromine or whatever thing. It's got to be either primary, and that's primary, right? Primary, meaning like the carbon only has the leaving group on it, or it can be methyl, like CH3 Br or iodine or something. Methyl. It can be primary or methyl. That's the rule. Otherwise, E2 happens. And E2 is again that thing that makes alkenes. So let's show an example of this bad thing that can happen. Okay. So if you have secondary or tertiary, it'll do E2. So primary or methyl, this works wonderfully. Okay. All right. So let's show a bad example. Bad example. Okay. So a bad example would be if I have like a secondary bromide. Secondary bromide, and I'm going to react it with lithium, for example, plus C. Okay, so this alkynyl anion, right? This is, and you might think, what would it possibly make, right? Well, if you want, what you probably want it to do is do an SN2 reaction, right? You want that carbon to attack that carbon and kick off the leaving group, right? So what you want to do, circle lone pair, attack the carbon and make kind of like that, right? Let's make that a little larger just so you can see it. That's kind of your goal, is this attacks there, kicks off the leaving group. But the problem is that this is a very good nucleophile, but it's also a good base. So this does not happen. And what happens instead? E2 happens. So what actually happens is going to be, essentially this is going to be a base, take off the neighboring proton and kick off the leaving group. So what actually happens is, under these conditions, is it grabs the proton. So this is going to be an E2 reaction, and E2 reaction is this base takes the proton, makes a double bond, kicks off the leaving group, and you get an alkene product, right? And that's not what we wanted. I mean, we were actually hoping to get an SN2. Okay, and then the product is just the alkyne. There's an ethyl group on there, right? Okay, all right. So what's the rule then? We'll go back to the rule. The rule is that if this only works if your alkyl halide, which is the thing you're attacking, is primary or methyl. Okay, secondary like this, or tertiary, like if you have an extra carbon, it actually does not do SN2 and it does E2. And usually E2 is undesired here, right? Okay, good. All right, cool. Anybody remember, before we go on, what are the, think of organic 1. You can attack, you can do SN2. Anything else you can attack? Like think about Grignards. Anybody remember Grignard reagents from organic 1? Because this is kind of like a Grignard. It's kind of like a metal attached to a carbon. Any other functional groups we can attack rather than just a boring old alkyl halide? Anybody know? Think about Grignards. What do Grignards do? I'll show it on the next page. But anybody from the chat? Functional groups that a Grignard attacks. So we're on 5 still. Grignards, similar to Grignard. And a Grignard was RMGBr from organic 1. From organic 1, we learned that Grignards react with basically three functional groups: ketones, aldehydes, and epoxides. Okay. And you should review this from the what you need to know from organic 1 thing that's on the website, and the key's up there also. But anyway, alkynes do the same thing, so let's show that now. So alkynes do this also. So let's show an example. Let's show. Let me do one ketone or a Grignard example. Okay, ethyl Grignard, 2 carbons, ketone, like an acetone molecule. What did this do from organic 1? The ethyl can attack the ketone, and I'll just draw circle the lone pair. It's a nucleophile. Circle the lone pair is essentially the bond here. So I circle the bond. The bond attacks acetone, kicks electrons up, And you get, in the end, draw it larger, a tertiary alcohol, right? Okay, so you get this, this is the final product. Ethyl, 2 carbons, attacks the ketone, electrons go up, and you've essentially made this bond, right? Okay, and that's a squiggly line I'm drawing right there. Okay, cool. And of course, the intermediate is that this will be O minus. Let's draw that down here to review. So when this attacks, you get an intermediate that looks kind of like the product, O minus. And what does the O minus do to the water? It takes that proton. Okay, so the O minus lone pair takes a proton from water and you get the alcohol. Okay, so let's show how that works with alkynes now. Because alkynes do the same exact thing. Okay, so let's do an example. Nice big molecule. How do I rip off that proton? The terminal proton of an alkyne? There were 2 ways. Anybody remember? One of them is like something 2, strong base. It was either NH2, NaNH2, right? NaNH2, or you can use a super base called butyllithium, which is butyllithium, one of the strongest bases in the universe. Super base, 1, 2, 3. I drew too many carbons. Let's erase 1. 4 carbons, lithium. 4 carbons, 1, 2, 3, 4, lithium. Okay. All right. So how are we going to rip off that proton with this base? How do we do the mechanism of that? I circle the bond between the carbon and the lithium, and it's a strongly basic molecule. So I just circle this bond and go grab the proton. Okay, good. And what does that make? Base takes proton, leaves negative charge on the alkynyl anion. Cool. So my point here is that we can react with ketones and aldehydes and epoxides. We also saw on the last page, what was the thing we attacked on the last page? It was something with a leaving group, like called alkyl halide, right? But these also kind of act like Grignards, and it can attack ketones, aldehydes, and epoxides. So let's draw one. Let's draw, I don't know, let's pick one like methyl ethyl ketone. Okay, methyl ethyl, it's a ketone with a methyl group and an ethyl group, right? So what's this thing going to do to this molecule? It's going to do the same exact thing that the Grignard did to this acetone, this ketone up here. So the negative charge is going to attack the carbon with the ketone on it. Okay, electrons go up onto oxygen. And what's the intermediate going to look like? So this thing's now attached to this. So how do we draw that? I don't know. Maybe I'll draw the 4 carbons There's a million ways we can draw this thing. I'll draw O minus, O minus. And now I'm just going to have this thing kind of attached because it's attached. C, and then we have to be linear, make it linear. So C, triple bond C, isopropyl, which is a little thing up top. Okay? And then we got to grab a proton from water. So always the last step of these reactions is water, just like it was up here, which was, you know, water was the last step, H2O. O minus grabbed a proton from water. Okay, cool. So, and then the final product above was a, what functional group is it above? It was an alcohol. And the same thing here, the final product would be an alcohol. O minus that you created will grab a proton from water and make the alcohol. So now I just redraw this exactly, but now it's an alcohol. And there's your final product. Okay. Another thing about this, kind of an organic one concept, but the idea that, like, how, you know, if we're given the product, of this, how do we know that it was a ketone? This is also something in the review notes for organic one. How do we know that if this is the product, that the electrophile was a ketone? What are the giveaways for that? Well, one of them is where the squiggly line is. There's a squiggly line, right? That's a squiggly line. That's where the new thing is relative to the OH. Where the new thing is relative to the OH. And when that thing is right next up to the OH, it has to be a ketone or aldehyde. A ketone or aldehyde. Okay? And the alternative would be epoxide. And remember, epoxides are these things. We'll show that one in a second. And when you attack an epoxide as a electrophile, the thing that's different is where the squiggly line is and where the OH is. The OH is on the next door carbon. So keep that in mind. You know, this is really organic one stuff, but we're going to see it again as we proceed. All right, so this is a cool example. We were able to attack a ketone and make this thing, and then it grabbed a proton from water, made the final alcohol. Anybody know what these things are called? It's this thing with an O minus, because I'm going to see this all the time, and I want to give it a name. The thing with the O minus. Anybody remember? This is like the halfway point to the product. Not an alcohol. This is an alcohol, right? I just want to give this a name. You learned this in organic one, but you've probably forgotten the name of an O minus thing. It's called an alkoxide. Alkoxide, okay? Yeah, all right, so the alkoxide. All of these will have an alkoxide intermediate. Alkoxide, okay, good. So that was a ketone. And what is the product kind of alcohol? What kind of product do we get when we attack a ketone? Is this a primary alcohol, a secondary alcohol, or a tertiary alcohol? How many things are there? There's three. It's a tertiary alcohol. This is a tertiary alcohol, right? So tertiary alcohol is good evidence that you came from a ketone. Okay? Tertiary alcohol, good evidence that you came from a ketone. The other evidence that it's a ketone is the squiggly is next to the OH. Okay, good. So let's try aldehyde now. Let's try an aldehyde. Still on number 5, which is alkynyl anions. Let's try an aldehyde example. So we'll just make a random, boring alkyne. In this case, what we're going to do is we're going to react it with Na and H2. and an aldehyde. And water. So step 3 is water. Let's figure, I'm going to skip the mechanism and have you guys do it. I'll draw the product though. I'll draw the product. In words though, what's the mechanism? And let's just redraw this as a slightly different beast here. The base, NaNH2. You know, I love circling lone pairs. So we can say that this is essentially Na plus NH2 minus, right? And how many lone pairs are there on NH2 minus? It's Na plus. That's a plus, you know, Na plus, right? NH2 minus is dot 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 minus. It's Na plus NH2 minus with 2 dot dots, 2 lone pairs, right? I'll redraw this up here. Na plus NH2. That's what it is, right? Na plus NH2 dot dot minus. And you know, if you're going to draw the mechanism out, which you can do that now. It's a couple steps, right? The base takes off the proton. You make an alkynyl anion. Then your alkynyl anion will attack the aldehyde, kick the electrons up. Your final product, of course, is not a tertiary alcohol, but what kind of alcohol? That's a secondary alcohol, right? And where's the squiggly line? The squiggly, I mean, where's the CC bond you created? Because we made a CC bond from carbon to carbon, right? Where is it? Draw it. It's here, right? There's your squiggly line. And where is it relative to the OH? Oh, it's right next to the OH. That's always evidence of either an aldehyde or a ketone, is the squiggly being right up to the OH, right? It's an aldehyde. Cool. Let's try an epoxide. Any questions on this one? Okay, let's try an epoxide now. Let's draw a different alkyne. And we'll use the other base. Right now there's 2 bases. You're using NaNH2 or butyllithium. Okay, epoxide, scary, scary. So that's an epoxide. I'm not going to draw the mechanism. I'll let you do it. Happy to do the mechanism after class also if anybody wants me to, but to save time, I'm going to keep going. But I'll give you some hints on the mechanism. And what's the product going to look like? Let's just, in words, step through what happens. The base, and if we were going to draw, I'll just draw the first arrow, of course. This base will circle lone pair, or, there's a lone pair on carbon, essentially, right? But I can just circle the bond, and that's suggesting that the lone, that we're using the lone pair. Circle the bond, attack the proton, electrons go onto the carbon. That's the first step of the mechanism. That makes the alkynyl anion. That is super nucleophilic. Sees the epoxide. And what's the thing about attacking epoxides? Are we going to attack the left side, the non-hindered side, or are we going to attack the right side, the super hindered side? We're going to make a good nucleophile, and it's like, where am I going to attack? Left or right side of the epoxide? It's going to attack the left side. That's non-hindered, or yeah, it makes sense. You're going to attack the non-hindered side, which is the left side in this case. So the final product, and you can draw the mechanism. Alkyne. How many carbons are we adding? 1, 2, 3, 4, 5. We're starting in with 4. 1, 2, 3, 4. 4 plus 1, 2, 3, 4, 5 is 9. So if our product does not contain 9 carbons, we screwed up. And the thing is, when we attack from that carbon to this carbon, I'll draw the opening up arrow. That'll be part of your mechanism. The bond, you know, that carbon will attack this carbon, open up, and now that's going to be the product. Make sure you can draw out that mechanism. Now let's count. What should our carbon count be? I said 1, 2, 3, 4 plus 1, 2, 3, 4, 5 should be 9. Let's see if I screwed it up. 1, 2, 3, 4, 5, 6, 7, 8, 9. Wonderful that my math is correct. And where's the squiggly? Which bond got created here? That's right. There's a squiggly. And that was this squiggly. This squiggly, is that directly where the OH is, or is it looks like it's one away from the OH? And that is suggestive position of squiggly. Squiggly, how do you spell squiggly? Squiggly, I don't know. Squiggly suggests epoxide. Okay, position of the squiggly line suggests the epoxide. And so sometimes you're given the you know, this plus this, you got to figure out what we attack. And by seeing the squiggly and where the OH is, you can deduce, oh, it must be an epoxide, right? That was all practice on the sheets, the you know, what you need to know from Organic 1. If you got to practice this a little bit, you should do that you know, pretty soon, maybe by next time. And also, yeah, where's the squiggly here next to the OH, or went away from the OH? Whereas where's the squiggly here? It's right up where the OH is. That's the big difference between attacking an aldehyde and attacking an epoxide. Okay, good. Yeah, I'll scan these and put them on the iLearn so that if there's any, you know, arrows you need clarification on, you'll be able to, you know, I'd maybe watch the video again, and then, but you'll see the scanned version, and it'll be a little clear. Exam style synthesis problem. We're solving number 5. Okay, so say we have acetylene, and we need to make this primary alcohol here, and I say question mark, what are you going to do? In terms of a synthesis problem, you need to be able to essentially go from this molecule to that molecule. And how would we do that? I mean, you know, strategically, we can do that retrosynthesis idea. At least to plan the strategy, I think that's very useful. Like, where's the squigglies? We got a couple squigglies. Start with the squigglies. Like, I see 2 squigglies. I see a squiggly right there and a squiggly right there, right? And this squiggly, the left squiggly, kind of suggests not a ketone aldehyde or epoxide, but maybe an alkyl halide, right? Because there's no oxygen here. So maybe what the thing we're going to attack on this side is really just, you know, phenyl CH2Br, phenyl CH2Br, right? Phenyl CH2Br. Whereas the thing on the right, the squiggly is a next, not directly where the OH is, but it's like 1 carbon away. Does that suggest ketone aldehyde or epoxide? Where the squiggly is, and somebody said epoxide, and you're totally correct, because the squiggly is not right up to where the OH is, but it's on the carbon next door. And how many carbons will this epoxide be? How many carbons will the epoxide be? How many carbons are there? It looks like I got, this is a case where having your handout really helps. I see, carbon and carbon. That looks like a 2-carbon epoxide. Wonderful. Now we have a strategy. What's the strategy? What's this? Let's do the full synthesis real quick. We'll do a base. Pick your base. It could be NaNH2 or butyl lithium. I'm just going to say B dot dot to be generic. Maybe we can do phenyl. Yeah, pH is an abbreviation for a benzene. So this molecule is really benzene CH2Br, right? Okay, so what does this do? Base takes proton. I'll say assume the left proton, and then that would attack, kick off the leaving group, and then we would make that. Good. Now, how do we go from there to there? Oh, well, we figured that strategy out. Base. Let's draw this part out now. Pick a base. It's going to be, I'm just going to draw 3 steps. 1, 2, 3. Okay, what's the base? Your choice. It can be NaNH2 or butyl lithium. NaNH2. 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 And then how many carbons in the epoxide? Looks like it's a 2-carbon epoxide. How do you draw a 2-carbon epoxide? Draw 2 carbons in epoxide, right? And what's step 3 always? The last step of this? Because it base takes proton, carbon attacks the electrophile, and then step 3 is always water, H2O. Cool. Okay, so we're basically done, but I'm just gonna preview what we're gonna talk about next. I'm just gonna say number 6 is actually beyond this a little bit. It's gonna be reduction of alkynes, and then I'll continue next time. Reduction of alkynes. I'll just draw it so you're a little bit ready for it. There's gonna be 3 ways. 3 ways. There's 3 ways we can reduce them. I'm just going to draw what they are, and then we'll talk about the details next time. So here's an alkyne. There's 3 things we can do. A full reduction, a cis reduction, and a trans reduction. A full reduction, a cis reduction, and a trans reduction. So the full reduction just basically completely reduces it all the way down to an alkane. So it's an alkyne all the way down to an alkane. The cis reduction will make a cis alkene, and the trans reduction will make a trans alkene. So there's going to be basically 3 ways we can reduce alkynes, and I'll go through the mechanisms and all that stuff and the reagents, because I'm not even showing the reagents yet. But that's where we're going. Any questions? I'll stop the recording and I'll hang out for you guys. Stopping recording.